Well, hello. If you're watching this or listening to this, you must be one of my students. So I find the topic of GPS when talking about instrument navigation can be kind of a complicated and loaded topic as things can get really detailed really quickly. So I figured I'd put together a small video just so you can hear and see a bunch of different things having to do with GPS so you can learn it better. So we're going to start off just this lesson. So I hope that you have been able to study Chapter 9 of the Instrument Flying Handbook. This covers all this stuff that you'll need to know about GPS, and then it also talks about VOR and ADF as well. And then if you have that Jeppesen Instrument Commercial book, Chapter 2 Charlie will actually help you with this as well. And then I have a bold method article here if you'd like to learn more about WAAS, which we will talk about in a minute. Some things I'd like to cover in this lesson really quick. I'd like for you to understand what exactly GPS is, how it works, and how we utilize it in aviation, because it's a big part of our training nowadays. So we'll also cover what RAIM and WAAS are, and how we are going to use GPS in our Archers. So starting off, what is GPS? So GPS is short for Global Positioning System. This is what is called a satellite-based area navigation system. We shorten this to RNAV for simplicity. And you'll see this a lot during your instrument training, so keep that in mind. It's actually a pretty old system. It's an old idea. It was invented by the U.S. Department of Defense, and the project started in 1973, and it became fully operational in 1993 when all 24 of the satellites that are used for the system were shot into space. Now this number actually is about 33. So this was actually distributed to the public in 1983, but the U.S. military, since they were using it, they actually intentionally scrambled these signals to make them pretty decently inaccurate, so our enemies couldn't use them. So this was actually overturned in the year 2000 by President Clinton. So now we have, as civilians, the same GPS that the military uses. So over time, as this has become very reliable, it's become the primary navigation for civilians, both on the ground and in the air. I'm sure you use your GPS a lot when you're driving. I do, I know that, and while we fly. So GPS requires at least 3 satellites to calculate position using something called trilateration, which we will get into in a bit. Essentially, these are all related to time, as these satellites have these atomic clocks in them, and that's essentially what they broadcast. So these things provide latitude, longitude, and time or velocity for ground navigation. These are unaffected by weather because they're in space, and it's available worldwide. And something that the FAA and ICAO have started to call it is GNSS, which stands for Global Navigation Satellite System. So you can see here on the right, down the bottom, I have a little diagram of these satellites and how they kind of use what's called trilateration to find your position, which we will talk about in just a second. So how does it work? It needs satellites and a receiver. Pretty simple. So satellites have atomic clocks that broadcast constantly. They broadcast their position and the time that they were broadcasting. So this coded information is monitored by a receiver. So say your GPS in your car or in your phone, your plane. And this receiver compares that broadcast time with the signal's reception. So the time it was received. So it uses this trilateration concept to get information on latitude, longitude, and time. And then we also use it for altitude for aircraft, so we need an extra one. So I have a little video here that you can, it's just a little GIF that you can watch to show, it'll show all the satellites in space that they kind of move around. And it goes into a little bit about how it shows a little aircraft here and how those satellites use trilateration to pinpoint the exact location of an aircraft. And there's a little picture too. So GPS and aviation. So we need an extra satellite in view to account for altitude. And then we need at least one extra one to account for error. So at minimum, our GPSs in aviation use 5 satellites. So in order to figure out if we have enough satellites in view, we have something called RAIM. RAIM stands for Receiver Autonomous Integrity Monitoring. And essentially, this is just the GPS receiver is verifying the integrity of these satellite signals by comparing them to one another and knowing that if enough satellites are in range. So this will both warn the user if there's a corruption of a signal from a satellite, and also if there are not enough satellites in view to ensure this accurate GPS signal, because that's very important for us when we're flying IFR. So if RAIM is at any point lost or during flight, or if there is a predicted capability problem, then you'll need to use either another navigation method or you just have to cancel your flight altogether. So you can actually check for outages via NOTAM. They will be disseminated that way. Then we have something that is more recent in development called WAAS. WAAS stands for Wide Area Augmentation System. This is just designed to be a more accurate and integritous RAIM. And this actually will run in the background. So you don't actually need to do anything if you have RAIM like we do in our planes, or at WAAS, I'm sorry. So this, again, improves the accuracy and integrity of these satellite signals by integrating ground stations. So there's ground stations all around the United States. There are reference stations and then 2 master stations. So what happens is that the signals from the satellites they go to these reference stations. The reference stations see if there is any corrupted data. They send them over to master stations, and the master stations send them back out. So that means that you have the most accurate data that you can possibly have. So you can have better integrity with your GPS. So just like anything, sometimes there are outages. Outages will also be disseminated via NOTAM, and the same thing with RAIM. If WAAS isn't available, then approaches will not be available, the WAAS ones, and then you must use a different form of navigation. And if you don't have manual RAIM, that doesn't work. So just a note, GPS may not be approved for IFR use in every country, but it is available around the world because of how the satellites work. So just a brief overview of the G1000 GPS in our Piper Archers. So we have 2 separate GPS WAAS receivers in this plane. They are located on the top of the plane. You can see them when we go out and do our pre-flight. We can use the GPS on both the PFD and the MFD. We can use it via the Direct To button or via the Flight Plan button. We can input all of our things there. It'll show up on the HSI and on the moving map if we have that as our input in our flight plan, and it'll show up as a magenta line. So on our PFD, we can use the CDI soft key to toggle from VOR1, VOR2, localizer, ADF, and then to GPS. And we can also use this on the Aspen EFD1000 Pro backup. So that's that's our backup instrument system on the left. And we will do more of this out in the plane. So here are my references if you want to know where I got my information. And I cannot wait to talk with you more about this. Here's what you can study next. So Jeppesen, if you have this book, Chapter 8, it's all about RNAV approaches, what we'll do with our GPS. The Instrument Flying Handbook, Chapter 1, reading approach plates so you understand a little bit more about approaches themselves. And here are some handy articles to review about RNAV approaches. So thanks for listening. Can't wait to see you next time.